All right, welcome back everyone to today's Explainer. We're going to embark on an absolutely fascinating chronological journey through the engineering physics of light. And look, today we aren't just memorizing abstract textbook concepts, we're literally going to step into the shoes of history's greatest scientific detectives to figure out exactly how light behaves, and, more importantly, how we as engineers can actually manipulate it. So, let's dive right in. Here's our roadmap for today. We'll kick things off with wave interference, move through massive historical milestones like Newton's rings and Fraunhofer diffraction, explore gratings and resolving power, and then hit polarization basics. Finally, we'll wrap the whole thing up with a quick executive review.
Okay, Chapter 1, Wave Interference. This is really the bedrock stuff, the foundational behavior of light. So to really get a grip on interference, I want you to picture monochromatic light waves, light of just a single pure wavelength, overlapping in physical space. Visualize it exactly like dropping two identical pebbles into a perfectly still pond. As those ripples expand and eventually overlap, they interact with each other. Now, when the crests of two waves align perfectly, their amplitudes combine to create a much larger wave. In optics, we call this constructive interference, and what you see is a bright band of light. But if the crest of one wave perfectly aligns with the trough of another, they actually cancel each other out. Boom, destructive interference, resulting in a dark band. This simple idea of overlapping, colliding waves, that's the engine driving the entire rest of our explainer today.
Moving right along to Chapter 2, the Newton's rings experiment. Let's actually step into the lab with Sir Isaac Newton to decode how waves act at physical boundaries. This setup is just brilliant in its simplicity. Imagine a plano-convex lens, so flat on top, curved on the bottom, resting completely flat on a perfectly smooth glass plate. Monochromatic light comes streaming in from the right, hits a glass plate suspended at a 45-degree angle, and is reflected straight down. That light travels directly into this incredibly tiny wedge-shaped pocket of air trapped between the curved lens and the flat plate below it. And we get to observe the whole chain reaction from above through a microscope. Let's break down the actual physical procedures step by step to really lock in what's happening. First, our single wavelength light hits that 45-degree plate. Second, it gets directed straight downward into the air film. Third, and pay attention because this is where the magic happens. Part of that downward light reflects off the bottom curved surface of the lens, and part of it travels just a tiny fraction further and reflects off the top of the flat plane glass underneath. Finally, those two reflected rays travel back up and overlap. Because they've traveled slightly different distances, they interfere with one another, generating these stunning, alternating bright and dark circular rings. Which brings us to the fundamental math problem. The specific type of interference we get depends entirely on one variable, T, the microscopic thickness of that wedge of air at any given point. For a bright ring to form, the path difference has to satisfy a strict condition. 2 times the thickness T must equal an odd multiple of half the wavelength. Or, mathematically, 2T equals 2n minus 1 times lambda over 2. Conversely, you get a dark ring when 2T perfectly equals an integer multiple of the wavelength, or n times lambda. Since the thickness of that trapped air film naturally increases as you move outward from the center contact point, the interference pattern manifests as these perfect concentric rings. Chapter 3, Grimaldi and Fraunhofer diffraction. This is where things get a bit bendy. Okay, so we know what happens when light bounces between thin boundaries, but what happens when it hits a literal roadblock, or has to squeeze through a tiny slit? Historically, this was first observed by Francesco Grimaldi. His huge contribution was proving that light doesn't just stubbornly travel in perfectly straight lines, it bends. Think about how you can clearly hear someone talking out in the hallway even if you're deep inside a room, right? Sound waves naturally bend around the edges of the doorway. Well, Grimaldi proved that when light falls on an obstacle about the same size as its wavelength, it similarly bends right around the edges and leaks into the geometrical shadow. This bending of light, that's what we call diffraction. Now, decades later, Joseph von Fraunhofer created a specific, standardized configuration to study this perfectly. A flat plane wavefront of monochromatic light slams into a single slit of width E. As the light squeezes its way through the gap, it diffracts, bending outward in all possible directions. Fraunhofer then cleverly placed a convex lens right after the slit to catch and focus all those scattered, diffracted rays onto a specific focal plane on a screen. Now here's the wild part about the resulting intensity graph. Logically, you might expect just a wide, even smear of light on the screen, but no. Because of interference between those diffracted waves, we get this massive central peak, the principal maximum.
The math dictates that the vast majority of the light's intensity concentrates squarely right there in the dead center. As you move outward, the waves actually start canceling each other out, creating progressively weaker, tiny secondary maxima. Chapter 4, Gratings and Resolving Power. This is where we level up from basic physics to straight-up optical engineering. So what happens if we take our single slit and just multiply it? We get a diffraction grating. Look at the difference here. Comparing our previous single slit graph, which gave us that wide, blurry central maximum, to a diffraction grating is a massive transformation. By dramatically multiplying the number of slits to hundreds or even thousands, the interference becomes intensely selective. Those wide bumps are instantly transformed into these insanely sharp, precisely defined intensity peaks. And this massive sharpening effect introduces a critical performance metric for real-world optical instruments, resolving power. Basically, resolving power is just the capacity of an optical instrument to cleanly separate things that are uncomfortably close together, or, in the case of our grating, to definitively separate two incredibly closely spaced wavelengths of light. To actually see the physics of resolving power in action, imagine a light source firing off two almost perfectly identical wavelengths. Let's call them lambda, and lambda plus a tiny microscopic fraction d lambda. A standard prism or a single slit, it would just blur them together into one useless spot. But a high-quality grating successfully forms distinct, totally separate diffraction maxima for each wavelength. Because the peaks are so razor-sharp, we can easily distinguish the two different colors, which is literally the entire basis of modern optical spectrometry. Chapter 5, Polarization Basics. Time to control the actual physical orientation of the wave itself. Up until now, we've controlled wave intensity and we've controlled direction. Now we control orientation. See, unpolarized light is completely chaotic. Because light is an electromagnetic wave, its electric vectors normally vibrate in literally all possible directions perpendicular to the way it's traveling. But when we pass this chaotic light through a polarizer, we restrict that wave propagation down to just a single plane, like horizontally polarized light. Think of it exactly like trying to slide a frisbee through a vertical picket fence. If the frisbee is horizontal, crash, it doesn't get through. It only passes if you turn it perfectly parallel to the vertical gaps. That, in a nutshell, is polarization. All right, Chapter 6, Executive Review. Let's wrap this all up into the key takeaways. We've covered a ton of ground today, from ripples in a pond to the highly precise manipulation of light vectors. Here are your big 4 takeaways. 1. Interference creates distinct bright and dark patterns via overlapping waves, just like Newton's air film experiments proved. 2. Diffraction, thanks to Grimaldi, proves light actually bends around obstacles and slits. 3. By engineering diffraction gratings, we dramatically increase our resolving power, turning wide blurs into insanely sharp, measurable data points. And 4. Polarization allows us to restrict a wave's physical vibration to a single plane. And hey, remember, these aren't just dry textbook theories. These exact physics drive the engineering of the anti-reflective coatings on your camera lenses, the LCD displays on your monitors, and the advanced spectrometers we use to analyze distant galaxies. So as future engineers, you are inheriting an absolutely incredible toolkit that's been developed over centuries of observation. We've gone from Sir Isaac Newton analyzing glass plates on his desk to engineering unbelievably complex optical systems. The fundamental physics hasn't changed a bit, but our application of it is advancing every single day. So I'll leave you with this thought. Now that you know exactly how light interferes, diffracts, and polarizes, how are you going to manipulate it next? Thanks for tuning into this explainer, guys. Keep questioning, keep building, and I'll see you next time.